So today, we're talking about the invisible engine that runs basically everything in our modern world, optimization. It's the hidden science that makes your phone work, keeps the power grid stable. It's all about making things faster, better, and way more efficient. And it looks like this engine is about to get a massive, massive upgrade, based on some really cool new research. Let's dive in.
All right, let's start with a bit of a riddle. What on earth could a giant AI language model have in common with the electrical grid that's powering your lights right now? I mean, they seem like they're from completely different planets, right? One is all digital code, the other is physical wires and transformers.
Well, it turns out they both fundamentally depend on these incredibly complex optimization algorithms to even exist. Figuring out the absolute best way to train that AI or the most efficient way to send electricity across the country, that's all an optimization problem. And the breakthroughs we're going to cover today are taking this whole field to a completely new level.
So, first things first, let's talk about the one thing everybody in this field is chasing: pure, raw speed. How do you find the absolute best solution to a problem as fast as humanly, or rather, computationally possible?
The absolute holy grail for speed in this world is a concept called quadratic convergence. Okay, here's a simple way to think about it. Imagine you're looking for something. A pretty good search algorithm might cut your search area in half with every step, which is good. But with quadratic convergence, you're not just cutting it in half, you're slashing it by like 90% or more with every single step. You just rocket towards that perfect answer exponentially faster.
And this is exactly where some of this new research is so exciting. A paper on a technique called boundary bilinear control just proved that a really important algorithm called SQP can actually hit this incredible speed. We're talking about applying this to super complex physical systems, things like managing heat flow. But here's the real kicker: it works even if your first guess is kind of terrible, which makes it so much more reliable for real-world problems.
Okay, so speed is great. We love speed. But speed by itself isn't enough. The real world isn't some nice, clean computer simulation. It's a chaotic mess. So how do these new approaches handle all that chaos?
I mean, just think about what an algorithm has to deal with out there. Your data is never perfect. It's always noisy. You get random shocks to the system, there are a million different variables to track, and totally unpredictable stuff happens all the time. For a standard algorithm, that's an absolute nightmare.
And one of the biggest bad guys here is what's known as heavy-tailed noise. Let me give you an analogy. So you're planning a road trip. Most of the traffic you hit might cause a 5-minute delay. Annoying, but manageable. But then, once in a blue moon, you hit a delay that lasts for 5 days. Those extreme, insane outliers are heavy-tailed noise, and they can completely break a normal algorithm.
So, what's the fix? Well, some new research has a really clever idea. It's a method that uses something called a clipping operator. And in plain English, it basically tells the algorithm to just ignore those totally wild, off-the-charts noise events. It just clips them off. This is a huge deal, because it means a whole network of devices, like in the Internet of Things, can keep working together and find the right answer, even if their connection is full of that crazy, unpredictable static.
Now, it shouldn't be a surprise that these incredible advances in speed and being able to handle chaos are having a huge effect on maybe the biggest optimization puzzle of our time: artificial intelligence. Anyone who's even remotely close to the world of AI knows this problem all too well. Training one of these massive language models is just a colossal effort. We're talking months of time and millions of dollars, all getting burned up by the sheer amount of computing power it takes to optimize that model.
Okay, so check out how cool this solution is. It's from a paper called Grad Power. And instead of trying to rebuild everything from scratch, they found this one tiny, elegant tweak to the process. They just apply a simple transformation to the gradient, that's the signal the AI uses to learn, and it speeds up the whole training process like crazy. And you're not going to believe this. It can be done with a single line of code. One line. That's it. Incredible.
But it isn't just about going faster. It's also about how the AI is actually learning. And this is fascinating. Research is showing this fundamental difference between two of the most popular optimizers, SGD and Adam. Think of SGD as having a simplicity bias. It always prefers the simplest, most straightforward connections in the data. Adam, on the other hand, has a complexity bias. It's much more willing to hunt for those richer, more complicated patterns. And that means Adam is often way better at figuring out which patterns are real and which are just false correlations in messy data.
All right, another really powerful tool we got to talk about is reinforcement learning, or RL. And honestly, the best way to get it is to just think about how you'd teach a dog a new trick. The AI, the agent, tries something. And if it does the right thing, it gets a treat, a reward.
If it does the wrong thing, no treat. You do that millions of times, and eventually it learns the best strategy to get the most treats.
So researchers are now taking that exact same idea and applying it to really complex control systems. They're basically using reinforcement learning to teach an industrial control system how to tune itself in real time. It learns from its own performance in a messy, noisy environment and is constantly tweaking itself to stay as efficient as possible. It's basically a system that learns how to get better at its own job.
So let's kind of pull all these threads together. What actually happens when you combine algorithms that are faster, more robust against chaos, and are just plain smarter? Well, you get the toolkit you need to run the critical systems of the future.
Take something like a drone or a self-driving car. It has to make critical decisions in a fraction of a second. But these decisions aren't simply yes or no questions. It's juggling dozens of rules all at once. Stay stable, stay within safety limits, don't push the motors too hard. For a long time, solving that complex optimization problem in real time was a huge bottleneck.
Well, a really groundbreaking new approach basically just tosses that old method right out the window. Instead of trying to calculate the perfect move from scratch every single time, which is super slow, researchers have trained a neural network to basically give you the answer instantly. It's like having a universal formula for safe and smooth control that's always on and ready to go.
But, and this is a really important but, as we start to apply these incredible tools to real life, we are also getting a pretty serious reality check. A recent study tried to use machine learning to optimize the entire power grid for the country of Uruguay, and what they found was a huge wake-up call. The real-world data was just so much more complicated and messy than the clean data you get in a lab. So much so that the existing ML models really struggled. It just goes to show there's still a big gap between what works in theory and what works on our most critical infrastructure.
So after diving into all these different areas, the need for speed, taming chaos, smarter AI, and these giant real-world systems, what does it all add up to? What's the big picture here?
The takeaways are, frankly, incredibly exciting. Our algorithms are getting exponentially faster. They're becoming tough enough to actually handle the randomness of the real world. This is making our AI systems way more efficient to build and a lot more intelligent when they operate. And this isn't just academic stuff. These tools are right on the verge of totally revolutionizing everything from how we manage renewable energy to how autonomous robots work.
What we're seeing is the creation of this amazing new toolkit for optimization and control. It's giving us the power to manage unbelievably complex systems with a precision we've just never had before. And that leaves us with the ultimate question, really. We're building the tools, so what should we build with them?